This lesson is on least squares regression lines. So this is 3.2, part 2. Regression to the mean. Using technology is often the most convenient way to find the equation of a least squares regression line. But it is also possible to calculate the equation of the least squares regression line using only the means and the standard deviations of the two variables and their correlation. So when it says that using technology is the most convenient way, that means typing in your data into L1, L2, and getting your prediction equation. But you can also get your prediction equation, your equation for y hat, if you know the standard deviation of your y's, the standard deviation of your x's, and your correlation coefficient. That gives you your b, which is your slope, a, which is your y-intercept, is y bar, so the mean of all the y's, minus b, which is your slope, times x bar, which is the mean of all the x's. Okay, now I want you to hit pause and I want you to find your formula sheet. And once you find your formula sheet, I want you to hit play again. Okay, now that you've got your formula sheet, I want you to look on the front, about halfway down on the left. You see y hat equals b sub 0 plus b sub 1 times x. That is the same thing as what your calculator gives you as a plus bx. Their b is b sub 1, and their a, which is the y-intercept, is b sub 0, which makes sense because b sub 0 in any kind of science or calculus is always the initial value, so that makes sense that b sub 0 is your y-intercept because that's your initial value or your starting point. B sub 1 is your slope. Okay, and then if you stay on your formula sheet, look 2 formulas down from this one, and you'll see b sub 0 equals y hat minus b sub 1 x hat. That is the same formula for your y-intercept. They're just, again, using different letters. They're using b sub 0 instead of a, and they're using b sub 1 instead of b. But this formula right here is on your formula sheet. It's just in terms of b sub 0. Then if you'll go 2 formulas down from that, so we're now second from the bottom, you'll see b sub 1 equals r times the standard deviation of the y's over the standard deviation of the x's, which is your formula for slope. So yes, the formula sheet gives this information to you, but it gives it to you with b sub 1s and b sub 0s. But if you will just look at this guy who is on your formula sheet, you will know because of Math 1 and Math 2 and Math 3 that b sub 1 is your slope because he's the guy with the x. So when you find your b sub 1 formula, that's your formula for your slope. B sub 0 is your y-intercept, so you find your formula for b sub 0, and that's your formula for your y-intercept. Okay, so this looks like a mess, but they're giving you all of the formulas. Now, what information do I have to provide for you? I have to give you x bar, y bar, s sub x, s sub y, and r. If I give you that information, then you can write me the equation of your prediction for your prediction equation. Now, if I give you all the x's and all the y's, you're going to type them into L1, L2, and you're going to go stat, calc, and down to number 8, and get me the regression line that way. But if I give you this information, you have nothing to plug into your L1 and your L2. So you have to be able to find it this way. Okay, so keep your formula sheet close, and let's try one. Using feet to predict height. We have used data from a random sample of 15 high school students to investigate the relationship between foot length in centimeters and height in centimeters. The mean and the standard deviation of foot lengths, and we've got the mean and the standard deviation of the heights. And I'll also give you the correlation coefficient between the foot lengths and the heights. Now you can see from this R that that's not super strong, but it is moderately strong. So there is definitely a relationship here. It says find the equation of the least squares regression line for the predicting height from foot length. Okay, so if I write out my formulas, I've got my slope, which is b sub 1, r, standard deviation of y's, standard deviation of x's. Okay, so b sub 1 equals, see my r is 0.697, standard deviation of my y's, 10.69, standard deviation of my x's, 2.71. Okay, when I type that into my calculator, I get 2.75. And I really encourage you to hit pause throughout this video if you need to slow down and catch up, if you need to go type something in your calculator to make sure you're getting the right answers. Just remember that you have that option to slow it down or rewind it and hear something again. So what I have found right here is my slope. So now I'm going to find my y-intercept, which is b sub 0. So my formula on my formula sheet is y bar minus b sub 1 times x bar. So b sub 0 equals, if we go back up here, my y bar is 171.43 minus my b sub 1, which is my slope, times my x bar, 24.76. And again, I encourage you to pause this, type this in your calculator, make sure you get what I get, 103.34. And that is my y-intercept. Now, just to state the obvious, if you mess up your slope and you use that number in your y-intercept doesn't stand a chance. This is not difficult math, but slow down. Make sure you put your numbers in the right place. Really make sure that you pay attention to your details. So the equation of my line, y hat, because remember this is a prediction equation, and I put my y-intercept first, and then my slope. Now, let me tell you what I've noticed in the past. This is a fairly straightforward, fairly simple process. You have to use formulas that you don't need to memorize because they're on your formula sheet. So what I have noticed in the past is that students sort of skim over this, yeah, I've got it, I'm good, and then when I get to this one on the test, they totally blank. So please don't, there's only one example of this because we don't need to repeat this process over and over again. It's the same thing every time. But don't mistake the fact that there's only one of these in the notes. That doesn't represent its importance. It is extremely important that you make sure that you know that these formulas are available to you and how to use them and what they give you. Okay, the last thing we have to talk about for correlation is just a little correlation and regression wisdom. These are just sort of fun facts, food for thought. There are some really, really great multiple choice questions that can come out of this next section of the notes. Wink, wink, hint, hint. All right, here we go. The distinction between explanatory and response variables is important in regression. If we reverse the roles of x and y, we would get a very different least squares regression line. However, if we reverse the roles of x and y, we would have the same correlation coefficient. So this is data that we're looking at from the trucks, the Ford F-150 with the miles driven. So this is if I have miles driven on my x-axis and price on my y-axis. Got my data, drew my line, here's my equation. And there's my r squared, and I could square root that to get my r. Now what we've done over here is I have switched them. I have price on the x-axis and I have miles driven on the y-axis. You can see, compare the dots, compare the actual physical line. That's a very different line. And you can also see I have a different y-intercept and a different slope. I have two different prediction equations. What this second one is going to do is it's going to say, okay, if I know the price, it'll predict the number of miles it has on it. But I do want to point out, do you see that you have the same r squared, which means that you have the same r. So flipping the x's and the y's will give me a different scatter plot and a different prediction equation. But it does not change my correlation coefficient or my r squared, my coefficient or my regression. Correlation and regression lines describe only linear relationships. Only linear relationships. But I can find an R and a prediction line for any set of data. You give me data, I don't care if it's linear or not. I'll give you a linear model that best fits it. That doesn't mean it's a good idea. You give me data that's not linear, I can find an R. That doesn't mean that it's linear. So check this out. These are 4 different graphs. This one looks fairly linear, a little spread out. This one, this part B, is definitely not linear. He is quadratic, but I can draw a straight line through those. Part C, I can draw a line. This is an outlier. He's going to pull the line up a little bit. That's fairly linear with one outlier. But check out this. Check out D. Now make sure you notice this point way over here. So he would kind of pretend that line was straight. Here's the thing. All 4 of these graphs have the exact same R. They all have an R of 0.816. Every single one of them have the exact same R. Now, is B a linear model? No. Should D be a linear model? Absolutely not. Now here's just one step farther. The least squares regression line for each association is exactly the same. All 4 of these graphs have the exact same prediction equation. That's crazy. Because 2 out of the 4 are 100% not linear. Yet they have the same R as A and C. And they have the same exact equation. This illustrates the importance of graphing data before doing your calculations. Now I'm going to take that one step farther. Not just graphing your data, because if I L1, L2, D, or B, and I don't ever look at my data, I'm going to get a pretty solid R and a prediction equation. But if I took time to look at the data, or better yet, if I took time to look at the residual plot, I would see, oh heck no, a linear model is a terrible model for this data. But if you don't take the time to go plot the data, or better yet, to go look at the residual plot and look for that pattern, then you will have no idea that it's not linear. So the moral of the story is, just because it has a strong correlation does not mean that it's linear. Just because you can get a linear prediction equation does not mean that you should get a linear prediction equation. You need to look at the scatter plot of the data, and better yet, you need to look at the residual plot to check for that pattern. Okay, now let's talk about being resistant. So we're obviously talking about outliers. So remember the problem we did about the kids and the age at which they said their first word in month and their score on that test. So here's some data, and we've got two kids I want to talk about in particular. I got child number 18, I got child number 19. Now, child number 19 said its first word really early and had a really, really high score on the test. Child 18 said its first word really, really late compared to everybody else and had a lower than average score for what it was predicted to score on this standardized test. Both of them are considered outliers. They are both outliers. All right, now let's jump over here to the residual plot. You can see the residual here is big. But what about the residual for child number 18? Not quite as big. But if you look back at the scatter plot, you can see that child number 18 is an outlier. But if you look at the residual, it doesn't show up as much unless you look at the horizontal distance away from the group. Okay, now let's look down here. This line right here is your prediction equation. Now what they've done is this red line is your prediction equation without child number 19. So that's without this kid. So as we can guess, you take this kid out, the line's gonna pull farther south because child number 19 is what was pulling it north. Okay. Now let's talk about without child number 18. Now child number 18 is way down here. If I take him out, then my line can now cut through more of these points and not have to worry about being pulled down by child number 18. So which one affected the line the most? And that's child number 18, because my red and my green lines are really close. But my blue line and my green line have a huge difference. So child number 18, even though it doesn't have a huge residual, it affected the prediction equation much more than child number 19, which had a huge residual. Okay, so here's the deal, and this we conclude this in words on the next screen, but let's just talk about this for just a second. If you have an outlier that is an outlier horizontally, it will affect your y-hat, your prediction equation, much more drastically than an outlier that is an outlier because of a vertical distance. Okay. All right, so let's see if we can sort of sum this all up. An outlier is an observation that lies outside the overall pattern of the other observations. So that's child 18 and 19. Points that are an outlier in the y direction, that's vertical, that's child number 19, but not in the x direction, have larger residuals. And look back, didn't child number 19, who was a vertical outlier, he had a bigger residual than child 18. Vice versa, they don't necessarily have as large of a residual. So points that are an outlier in the x direction, that's child number 18, if he's an outlier in the x direction, he doesn't necessarily have as large a residual because he's closer to the line, because he's pulled the line towards him. An observation is influential. Okay, now let's think about this before we read anymore. Which point was more influential to our line? Child 19 or child 18? Child 18. The reason is because he had an outlier in the horizontal direction, in the X direction. Okay, so let's pick up with this paragraph again. An observation is influential for statistical calculation if removing it would markedly or drastically or significantly change the results of the calculation. Points that are outliers in the X direction of a scatter plot are often more influential to the least squares regression line than if you had an outlier in the Y direction. So child number 18 is more influential to our line than child number 19. Points that are outliers in the X direction are influential. Points that are outliers in the Y direction are not influential, but they'll have a bigger what? A bigger residual. We didn't need the distinction between outliers and influential observations in Chapter 1 because we weren't talking about two different pieces of data. A single large salary that pulls up the mean salary for a group of workers is an outlier because it lies far above the other salaries. It's also influential because the mean changes when you add in that CEO's salary. Not only is it going to be an outlier because it's far away from all the others, but it's going to drastically affect the overall average because the mean is not resistant. He is influenced by outliers. In the regression setting, however, not all outliers are influential. This is just recapping what we've already talked about. The least squares line is most likely to be heavily influenced by observations that are outliers in the X direction. One more time. The least squares regression line is most likely to be heavily influenced by observations that are outliers in the X direction. Child number 18. Influential points often have small residuals. Influential points, that's child number 18, and didn't it have a small residual? And here's why. They are so influential, they pull the line towards themselves. So they're not as far from the line as, say, child number 19. In other words, don't just look at a residual plot because you may miss influential points. And last but not least, please make sure you know that when you find these prediction equations and when you find these R values and these R squareds and you interpret all this stuff, you are simply finding an association, relationship between two variables. You are not finding causation. Having a cell phone will not cause you to do well on the AP statistics exam, but there is a relationship between having a cell phone and students who do well on the AP statistics exam. So watch out for words like cause in a multiple choice question or in a follow-up question to a free response question. Okay, that's it for this. Again, feel free to rewind, feel free to watch it again, go back and watch a piece that didn't sit well with you. I hope you took really good notes. Go do the homework and make sure you check your answers online and come see me if you have any questions.